This is banked curve, the simple version where you just use one triangle. This is the way I learned it. Inclined plane and banked curve both involve a ramp with an object on this ramp that wants to slide down. The downward force is the same whether you're talking about an inclined plane where something just slides down and has friction pulling it back. But if you have a banked curve, instead of just having friction pulling it back, you have the centrifugal force or centrifugal force. So inclined plane and banked curve both have the same downward force, they just have a different backward force. Otherwise, they're the same. Okay, if you got a ball on a rope here and you're spinning it around, mass times acceleration equals your force. Your acceleration is v squared over r. So it's just mass times v squared over r equals your force. So you can imagine as you increase your velocity, as you swing this ball around on a rope, that will, you square that, so that will significantly increase your force. And so if you have the same velocity, but you're doing it over a really small radius, that will also increase your force. In reality, if you're swinging this ball on a rope over your head here on Earth, you're going to have gravity pulling down right here, so it's not going to be completely horizontal. There will be a little bit of downward angle there. That's only tangentially related to the equations I'm going to show, but I just wanted to throw that in there to be thorough. So here's what we can do here is take our mass times acceleration equals force. We multiply that by cos theta. Here's the logic. Again, this is a single triangle method because it just involves one triangle or one ramp. Imagine swinging this ball on a rope over your head. This little rectangle here with the springs in it, that represents a tensile scale or a tension scale, so you know how much force is on the rope. Say if you're in outer space or something, in a space station, you're swinging this over your head, it wants to go out completely horizontal. So cosine of 0 degrees, 0 degrees is horizontal. That means there's the full force on this scale right here, or full tension on the rope. Now, if we're swinging this around our heads and there's a banked curve here, say 45 degrees or so, this ball wants to go completely horizontal, but it can't. It's being partially blocked by this ramp. And so we look at the angle right here of theta, and that would be 45 degrees. So there's going to be some decreased force or decreased tension on that rope right there. Take it to the extreme, take it up to 90 degrees right here. We're swinging this ball over our head. And it's going around in a circle, but someone put a big wall up next to us, so we're inside of a big cylinder, and this ball is pressed up against a cylinder, so now we're not going to have any force there, and this ball is just going to fall. So I wrote, here I wrote one arrow down for force, showing there's a little decrease in force, and here there's two arrows down showing a great big decrease in force, but actually there's no force because cos 90 equals 0. So we just take that same concept over here to a car or a marble or something going around a curve, and it's on an inclined plane right there, or a banked curve as it travels away from us. The force wanting to bring this object down here will be your, I wrote F with a downward arrow, that's mg sine of theta, because mg is the downward force. You just multiply that by sine of theta, because if theta is 90 degrees, and that would mean you're going to have full force or the full mg pushing down. So imagine this ramp right here, and that angle goes up to 90 degrees. You stick a scale under there, you're going to get the full force of this block. As theta gets smaller and smaller, sine of 90 gets smaller and smaller. Eventually it gets down to 0 degrees or horizontal, and you have a scale underneath this block here. Then it's not going to register any force if the block is horizontal, and that is neglecting friction. Now the force pushing this block backwards is just going to be your m, your mass, times v squared over r times cos theta, as I just showed. That's the force with the up arrow. So what we do is just set our downward force equal to our upward force. Mg sine theta equals the m times v squared over r cos theta. Take your cos, bring it over here and put it under sine. So you got sine theta over cos theta. Take your g, bring it over here and put it under your r. The masses will cancel because you got one on each side. You end up with sine theta over cos theta equals v squared over rg. Sine theta over cos theta equals tan theta. That equals v squared over rg. Using this information here now, if you know the object's velocity, or the radius or gravity or the angle that you want. You just plug in all the variables and you solve for whichever variable you don't have. If you're also dealing with friction holding this block back here, then you just add the frictional force to your centrifugal force. You can see my other video where I showed how to derive the formula for a inclined plane where the friction is holding it back. It's nice knowing how to derive these formulas because if you ever forget them, which I did, then I didn't need to look them up. I could just rederive them, so that was nice. There is a method to derive this as well that involves 4 triangles that are all joined together. It's far more complicated, I think, when you see all the triangles and the vectors. So this right here may technically not be approved when you use just a single triangle method, but it allows you to use just basic logic to rederive these formulas if you ever forget them, so that's nice.